What's going on, everybody? Zane here, back with another video. For this one, we're going to go over question number 146, which is LRU cache. LRU is representing least recently used cache. So in this problem here, what we're being told is to design a data structure that follows the constraints of the least recently used cache. Now, although we're being asked to design the data structure, there's actually a much more efficient way of solving this problem. Because in the end, what we want to do is, if we had an example such as the following, where we're putting two integers into some cache, we'll say 1 and 1, and then we'll put 2 and 2, then the next one would be 3 and 3, and these could be any values. And we're using two integers, so because that's what the key and value are. They're both ints. So we put in these values, and now if our capacity was equal to 3, that means that our capacity has been reached. So now LRU is going to come in, least recently used is going to come in when we need to do our fourth operation, where now we need to add in another value such as 4, but we can't do that because we are already at capacity. So now LRU comes in by taking away the oldest value and then adding the next value. So when we're considering this question, and any question really, we need to think about what type of data types we need to use. So here we're seeing puts and gets. We're also seeing a runtime of O1, and we're seeing a lot of key value stuff. So right off the bat, we know that we need to use some sort of mapping. But we also have the LRU portion, which is telling us that, hey, we need to do something with the head when we have a new tail. So that is going to tell us that we need a doubly linked list. Now, before I go into explaining this, we need to establish the fact that once we have our data types, we can use the built-in functions of Java to our advantage. We don't need to necessarily create a new node class and then establish the variables there and then link the heads and tails. We don't need to do that right now. What we could do is we can extend an existing class called the linked hash map, because essentially that's what we're doing. We're going to be dealing with a doubly linked list and a hash map of some sort. So we can just extend the existing collection of the linked hash map, and this hash map will be of type integer and integer, because our key and values are both ints. Now that we've done that, what we can do now is we need to establish a capacity. So although we're being given capacity inside of our public LRU cache, let's first initialize it. And then we'll say that this capacity is equal to capacity. And now we need to take care of the access order. So what we can do now is we can use the parent class's methods or functions. In order to do that, we would use the super keyword. And what super is doing is just using the parent class's initial methods. So whatever is part of the linked hash map class, that's what's going to be used after this statement. So I'll just say super, and then I'll overload the linked hash map method to be capacity, and then some decimal value or some float value, and a value of true or false. Now, in this case, I'm going to put true. And the reason for that is because I want the access order to be specific to its access and not insertion. So when true equals access order, when false equals insertion order. So since we're dealing with LRU, we need to use the access order, which is why I have true here, and I'm overloading it with the capacity of float and true. You can read a little bit more about linked hash maps. You'll see that I have some tabs open just reading up on what exactly load factors are and whatnot. But I saw that in the solution for the LRU cache, people were using 0.75f, and it looks like that seems to be a good trade-off in terms of time and space. Like right here, as a general rule, the default load factor offers a good trade-off between time and space costs. So if we were optimizing something, perhaps 0.75 would be better, but in this case, it does not matter. So I'm going to overload it so that this is really the main thing we care about. We want the access order. That's the whole point of LRU Cache, which is why we're extending this class to the linked hash map class, so we can take advantage of that property. So now that we've done that, we're done with our initializing of the public LRU cache. Now we can use super the rest of our linked hash map class. So what I can do now is, since we need to return the value from our map, we can say return and then super.get the value of the key. And if that is equal to null, then return -1. Because we say here that if the key does not exist, then just return -1. So if it's a null, then we'll return -1. Otherwise, if the super.get, otherwise we'll just return super.get key. Now that's it for our get function, because we're again using the get function from the linked hash map class. We're extending that and using the super as our parent class's method for our parent class's method. Now, on our last piece here, we have our put. This is a void, so we can do a simple super.put key and value. Now, if we were to run this, we're not necessarily going to be finished, although it looks like we're almost there, but there's still a major aspect, which is, although we have our access order proper, we need to now be able to remove our oldest key. Like in the example I'd shown below, if we have our fourth entry in a capacity of 3, we need to remove the top value. So what we could do is we'll create a function, and it'll be a Boolean function, and we'll say remove eldest key. And inside of here, we're going to pass in a map entry of type integer and integer, which is essentially going to be this linked hash map. And we'll just call this map. And we'll say that this will return true if the size is greater than the capacity. So we want to remove the oldest key if and only if the size of our map is greater than the capacity, or the size of our LRU cache is greater than the capacity. So if we try to run this, we're still going to get an error here because there's still one thing missing, and that is we need to actually override this function. And the reason we're overriding is because we don't want to actually use the parent class's function. We just want it to do its own thing. So we'll run this now, and we'll see that there does not implement the method from a super type. Okay, that's fine. What we can do here is we'll change this to a protected and see if protected static might work. Okay, so there's an issue here, and I would assume that it's because I'm using the wrongest. Yes, so I'm using the wrong name. So remove, so I'm going to change this back to public. Let's try that again. And now it's saying that cannot override. So now I'll change this back to protected and take this off. There we go. So this is something that I've learned and I wanted to share, and I'm glad these errors occurred, because when we're trying to override something, it needs to be in a specific type when we're doing the signature of the class or of the method. So if I was to do public, I just want to see if that works out. So public still works. So just make sure if you're overriding something, it needs to have the exact name of the parent class's method. Now, once we've overridden that, we can say, okay, instead of doing what you typically do, we're going to override the signature with this and return only if the size is greater than the capacity. And then when we submit this, we should be good to go. So just to recap real quick, we already have our LRU cache. We're extending the linked hash map class, passing in an integer and an integer, initialize our capacity. Inside of our public LRU cache, we'll set the capacity to equal capacity, just like we typically do for any class creating of the constructor. And then we'll super the capacity, we'll super and overload the by passing in the capacity, some load factor, in this case we're just using the float of 1, and true only because we want the access order, not the insertion order. That's the whole property of the LRU. Then in our get, we can just use our parent class's super, so we can get the value of our key, and if that's null, then return -1. Otherwise, we can return the key's value. Alternatively, I think what we could do is we can return super.get or default, and we'll get the value of the key, or we'll return -1. Now let's just make sure that works. Yeah, so this is a little bit cleaner. And then for put, we'll just do our super.put, and we override the remove eldest entry method, and only do that if the size is greater than the capacity. Anyways, guys, that's it for this one. If you have any comments, questions, feedback, please let me know in the comments below. Otherwise, hit that like and subscribe button, show me some love, and I'll see you in the next one. Peace.